Okay, thanks. So, yeah, I'm Peter Gregory. I'm from Teesside University. Stephen's from the stationary office, and you'll have to ask me later if you're interested in what that means. So the title of the paper is Domain Model Acquisition in the Presence of Static Relations in the LOP system. So it's going to be something about statics. I hope everybody knows what they are. Domain model acquisition. Okay, so this is a learning task, but we're not learning control knowledge. We're not learning how to plan. We're learning what the domain model actually is. Okay, so we're given some observations. We want to calculate a domain model, and observations can be of various different things. So we can have action traces, as we do. You could have state information. We don't have that. And you can have things like predicate names. We don't have that either. Where would you want to use this? So either is a way of encoding domain models. So writing PDDL is hard, error prone. Or you can create a declarative model of an existing control system that you have access to, right? So you know how to move the various parts, but you don't know how that logically fits together in some kind of system where you could provide planning for. Okay. Also, in work that I've generalized to the general game playing area, so you can translate between formalisms. So you can imagine in planning maybe translating from so if you had PDDL kind of 2.2 or something like that, and you wanted to convert back to strips as best you could, then you could use this as well. Okay, so the previous work we'll see a little bit of. So Lockham and Lockham 2 are unique in these domain model acquisition programs in that they learn domain models from only action traces. Okay, so we don't have any other information except the action trace. Okay, so that seems like a hard problem. So if we're going to learn anything from these things, then we're going to have to make some assumptions about what the target model is. Okay, and the assumption that we make is that each object type in the output model can be represented as a state machine with some particular properties, right? So each edge label can only appear once in each state machine, and these edge labels are indexed operator arguments, okay? So we'll see a little example of how this works. So this is kind of the schematic diagram, right? So we get a load of example plans in, we do lock them in the middle, and then we get some stuff out, okay? Okay, so here's an example from driver log. This is an example action trace, and luckily in this example, the driver's in all of the things, so let's just consider the driver. Okay, there's 4 types of transition for the driver. So there's board.1, drive.1, disembark.1, and walk.1. So the .1 refers to its position in the argument list of the actions. Okay. So what we're going to do, we're going to build a state machine incrementally that represents this driver. Okay, so we start by saying, well, he's got these transitions and they might be independent, right? So he starts in some state before he boards something and he ends in another completely arbitrary state. But we know that if we see consecutive states, then we can say the end state of the first thing we've seen, the first action is the start state of the second action. Okay, so what we're going to do, we're going to go through this list and we're going to merge states incrementally. Okay, so we've seen a board and then we've seen a drive. Okay, so we can now say, well, this means that the end state of board is the start state of drive. And then we see another drive, so we can say, well, the end state of drive must be the start state of drive. So that means we got a little loop. Okay, then we see a disembark. Okay, so that means that after a drive, you can disembark something. Okay, and we keep doing this. And then we end up with this state machine. And finally, after we've walked somewhere, we can get into a different truck, which makes this merge happen. Okay. So this state machine at the top describes the behavior of a driver in the driver log domain. I hope that's clear to everyone. It's not quite finished. Okay, so we've got these things called object parameters. There are associations between the different objects. Okay, that's what we do in planning. Otherwise, the state would be just a set of completely disconnected things. And the colors here show us what these connections are. So between the first two actions, there's a lock 1, then the next two, there's a lock 2. Okay, and so what we do, we label these states with types. Okay, so in this state on the left, when our driver's walking around, he's associated with a location. When he boards the truck, he's associated with a truck and a location. Okay, so this is prior work, so this all works fine. And then we can convert this to PDDL by simply taking the states and creating a driver state for each one and associating with it the objects in the action parameters. Okay, so this is the action that we get. Well, we should notice some kind of problem with that, and we'll see that now. So that it induces this initial state and goal state, and when we plan with these things, then we get this thing here, right? So this was our input plan on the left-hand side. Our output plan on the right-hand side is shorter, so that's a bad thing. And this is why? Because we don't have static information, right? So there's an underlying path map in the driver log domain, and we don't have that. Okay, so we don't want to produce invalid plans. We want to produce a domain that's correct, and we can produce valid plans from. Okay, so we're encoding the dynamic aspects of the domain, but not the statics. Okay, so this gives us an idea for a solution. So if the invalid plans are shorter, right? So if this was an optimal plan on the left-hand side, and we find something shorter, then that gives us a hint that we can do something to the model to refine it in some way. Okay, but how can we even guess what form the statics might be in? Okay, so I want to present a creative interpretation of what actions do. Okay, so we can think, now we've got these state machines, we have all these parameters in an action. So we've got 3 parameters here, and every time the action is applied, they're going to perform some little dance, right? Okay, so these things are now going to go around in a little circle, and we're going to get a new object parameter here. Okay, now some objects don't want to dance with each other, right? So we've got some shy dancers who don't want to dance in this particular combination, and so what we have are these things called statics, which define who wants to dance with each other. Okay, so the thing at the bottom is what we want to really be thinking about. So all static relations really do is restrict to the combinations of ground actions that we're allowed for each operator, right? Therefore, all of the statics that we might define in the problem in terms of this kind of semantic way, like the road map, the path map, the things that are in lines, we can say every operator has a static predicate, and that static predicate has to define the ground operators that are admissible for that operator. Okay, so we don't just want to find any of those things, right? So we could say the scope of this relation is every fact, right? So take for example the rover's domain. So each of the rover has its own roadmap, right? Because it's got different functionalities, it can go in different places. In the driver log domain, that's not true. Okay, so if we defined the static relation over the drivers and the locations, we could do it, but we need a lot more facts in our static, right? And if what we're doing here is helping a domain designer to make his domain, we don't want him to have to specify the same roadmap over and over again for every combination of objects. Okay, so we want to find the smallest relation for each operator that we can do that defines the actual ground instances. Okay, so for driver log, we've got 2 statics, one for the drive, and one for the walk. And given a candidate minimum static relation, we can reformulate one of these input problems, right? So we add something to the domain that Lockham produces, and we also add something to this initial state here, right? So what we're doing, we're taking the input optimal plan, and we're adding a static for every one of the combinations in the input plan, right? So we're defining probably a subset of the original relation that's defined by the input plans. Okay, so now we see roughly the contribution of this paper, which is the LOP algorithm. Okay, so we're going to do three things. The first thing is the most important. So we're going to identify a minimum static relation for each operator. The next two things are just helpful additions. So we're going to test whether each identified relation is universal. And what we mean by that is whether the relation holds for all instances of the domain. Okay, so that's common in some things. And thirdly, we're going to test whether each relation can be split into smaller relations. Okay, so that's useful for some domains. Okay, but really the most important thing is the first. Okay, and all of these things rely on a routine for testing if what we say is optimality is preserved. Okay, so now you can think of Lockham as not only producing a learnt domain, but it also produces a set of induced problems, right? So we've got these input plans, and then we produce the equivalent problems files with respect to what that domain says there. Okay, and in terms of preserving optimality, well, we take all of our optimal plans on the left-hand side and all of our induced problems, and we one by one put them into an optimal planner with some candidate minimum static relations, and we test whether the induced solution length is less than the optimal plan length. If it is less, then we reject that candidate set of relations, right? And then we need to refine it some way. Okay. If no, we continue until we get to the bottom of this stack, and then we say, hooray, they look fine. Okay. So this is just the same thing written in algorithmic form. I think everybody understood the outline. Okay, so this is a positive example. So we have a walk static, which is between the driver, the two locations. This will preserve optimality, but it's not the minimum one, right? But it's still okay. Yeah, I mean, it still preserves optimality. This is a negative example, right? So in here, we've got only a static on L1. So this means that the locations that you go from are restricted, but not the locations that you go to. Okay, so you might only be able to start in location 1, but you can go to anywhere from there, right? So that's not going to preserve optimality. Okay, so how do we use this algorithm to find minimal static relations? Well, it's quite a simple thing. We start by assuming that all the parameters of an operator are in the minimal static relation. And then one by one, we take them out. We test whether this preserves optimality. If it does, then we throw that one away. We don't need it. If it fails to preserve optimality, we have to put it back in because it was necessary for the static relation. Okay? So this is what this algorithm says. And just to give an example of this, one of the great things about working with Lockham is it gives you surprising results all the time. Okay? So this is the zoom operator from Xenotravel. Okay? So we're flying a plane from location 1 to location 2, and the F's is fuel levels, right? So Zoom uses more than 1 unit of fuel, so it jumps from 3 to 1 at the end, right? So we go through, we say, well, we don't need the plane, that's not part of the statics. The locations in Xeno are not restricted, so you can fly between anywhere you want. F3 doesn't preserve optimality, so we need this guy. And then F2, oh, hang on, we weren't expecting that result because in the real domain, F2 is part of the static relation, right? But in fact, all you're doing is going from F3 to F1, right? So the static relation that it encodes is that, you know, the n plus 2 rather than the n plus 1. Okay, so in fact this shows a bit of redundancy in the parameters in the xenotravel domain. Okay, so one thing that this means is that it's quite hard to evaluate Lockham-based systems because you have to do a lot of hand looking to make sure that these things are actually the same or not. Okay, so universal static relations, these are things like the fuel levels where we encode so numbers or regular structures like grids, and they're the same for all instances. Okay, so to test if we have these universal relations, we simply take all of the static relations from every one of the problem instances and put them all in the new files and test for optimality again. Okay, so I'm not going to say too much about that. Details in the paper. And sometimes we might want to split these statics. So if we've got something that makes sense to be two things, so in FreeCell you have two different number systems in the same operators, then you might want to do that. So we do this by testing all the partitions of the static relation, and we rank them by, we value them by the rank of the partition. Details are in the paper again. Here's a surprise. So there's lots of surprises with using Lockham. Some of what we thought was the static information, Lockham originally has managed to encode as dynamic information, right? So this is a number system in FreeCell, okay? So it incorporates so one number which is the current number that you're looking at, and then there's relationships between predecessors and successors, and so effectively it moves the current number up and down this list, updating. So if we increase 3, then we would get successor 3, 4, current 4, and then predecessor 5, 4. Okay, so things that we expected to see as results came out to be encoded as dynamic facts, right? So again, this just adds another layer of complexity into evaluating these things. Okay, so here's a big table of results. Okay, so we've got a load of domains down the side. An interesting thing to look at are the ticks and crosses. So the crosses mean that Lockham 2 was incapable of representing it from the plans. Normally this is due to dynamic many-to-many relationships, and you'll have to look at the Lockham 2 paper to understand why that's a big problem for us. And the ticks with stars mean that that was true, but we could modify the input so it wasn't true anymore, right? So I went to some lengths. I couldn't carry on for an infinite amount of time to do that. These columns here said I won't point. These are the number of errors that are generated by the LOP system, which is very small. Normally we're making nothing. There's some nice reasons for why we make some. You can read about that in the paper. And just to add, the final 3 columns show that if we use a satisficing planner rather than an optimal one, we can still get almost the same results. Okay. The Myconic paper you'll have to read about in the paper. And in conclusion, so we can now learn domains with static information. We got good coverage across IPC domains. Future work, dynamic many-to-many relationships, and something to do with action costs. And just to show you something about the complexity of what you get out. Any questions? You can ask about this if you like.